Hello, everyone. Welcome to the channel. I know I have been out of it for quite some time, but I've been posting more on my other channel. But this video is mostly because some of the members on my team asked me to do this. And to be honest, I was actually frustrated because of this. And this video is sort of made to let the people know how things happen in enterprises. So I was on a client project, big enterprise client, multi-team setup, cloud deployment, the whole thing. And we had this issue, or we still are having, I will tell you at the end. Services couldn't talk to each other, deployments were failing, half of the team was staring at the logs and had no idea what they were looking at. Nobody on the team except me could actually trace what was happening. Not because they weren't smart, they were, but because nobody had ever sat down and explained what the network actually looks like when you deploy something in a real client environment. They knew how to write code, they knew Docker, they knew Kubernetes even. But the moment you put them in front of the VPC with private subnets, a VPN connection, and a bunch of private endpoints, it's a complete blank stare. No one knows anything. And honestly, that's a gap I see on almost every team. And sometimes this knowledge is also required for managers, by the way. Networking is the one thing that gets skipped in almost every curriculum. Everyone learns HTTP, nobody learns what happens below that HTTP. So this video is for that team and for every team like it. We are going to cover networking from the ground up, but specifically through the lens of how real deployments work in real client environments, not theory, not textbook, the actual stuff you run into. We will cover what a VPC actually is, why everything lives in a private subnet, how services talk to each other, how VPNs and private endpoints work. And at the end, I'm going to walk you through the exact checklist you use to debug a network problem when nothing is talking. No cloud provider lock in either. These concepts work on AWS, Azure, GCP, all of them. The names change, the ideas don't. Before we talk about VPCs and private endpoints and all of that, we need a shared mental model. This section is fast. If you already know subnets, stay for the blast radius framing at the end. It reframes how you think about all of this. So let's start with the basics. So IP addresses and ports. Think of an IP address as a postal address. It tells the network where to deliver something. Think of a port as the apartment number inside that building. The address gets you to the building, the port gets you to the right door. So when your app connects to a database on port 5432, it's saying, go to this address, knock on the door 5432. Next is public versus private IPs. There are two worlds of IP addresses, public and private. Public IPs are globally routable. They live on the open internet. Anyone can reach them if they know the address. Private IPs are the opposite. They only exist inside a private network. You can have a machine with IP 10.0.1.45, and that address means absolutely nothing outside your network. Nobody on the internet can route to it. It doesn't exist to them. This is one of the most important concepts in the entire video. Write it down if you need to. Private IPs never route on the public internet ever. This is not a setting, this is not a configuration choice, it's how the internet is built. The entire range is 10.0 X point, X point, X, and such like that are reserved. Reserved means the internet will drop them, full stop. This is exactly why your services inside a cloud network can talk to each other freely. They are all using private IPs, but you need special infrastructure to let outside traffic in. We'll cover that. And the next question is, what is a subnet? Your network is a city. A subnet is a neighborhood inside that city. You have a block of IP addresses. Let's say your network owns everything from 10.0.0.0 to 10.0.255.255. That's a lot of addresses. A subnet is just you saying this chunk of addresses is one neighborhood, this other chunk is another neighborhood. Why do you carve it up? A few reasons. Organization. You put your web servers in one subnet, your database in another, your internal tools in another. Routing control. You can give different subnets different rules about where they are allowed to send traffic. And most importantly, the blast radius control. Blast radius is a concept from security. If an attacker gets into one subnet, how much damage can they do? If everything is in one flat network, the answer is everything. If you have segmented properly, the answer is just that one neighborhood. They are contained. This is the real reason we care about subnets. Then we have the CIDR notations, just enough to read it. You're going to see things like 1.0.1.0 slash 24. That's a CIDR notation. Here's all you need to know. The number after the slash tells you how many bits are locked. The more bits locked, the fewer addresses you have. Slash 24 means the first 24 bits are fixed. You get 256 addresses. You will see this constantly. Slash 16 means more flexibility. That's 65,536 addresses. That's usually the whole VPC range. Slash 32 is exactly one IP address. You will see this in security rules when you are whitelisting specific machines. You don't need to calculate this from memory. Every cloud provider has a CIDR calculator. Just know how to read it when you see it. That's your mental model. IP IPs are addresses, ports are doors, private IP stays private, subnets are neighborhoods, segment for blast radius, and read CIDR. Everything else we cover builds on these six things. A VPC, virtual private cloud, is your private data center rented from a cloud provider. AWS calls it VPC, Azure calls it virtual network or VNet, GCP also calls it VPC. The names are almost identical, the concept is completely identical. You tell the cloud provider, I want a private network. Here's the IP range I want to use, and they give you an isolated private network that nobody else can touch. Your resources live inside it. Traffic between them stays inside it by default. Think of it as you bought a floor in a massive building. The building is the cloud provider's data center. Your floor is completely walled off from every other tenant. You control what comes in, what goes out, and who can talk to who. Inside your VPC, you create subnets, and there are two fundamental types. A public subnet has a route to the internet. Things that need to be reachable from the outside world lives here. Your load balancers, your bastion host, or we also call it as jump hosts for SSH access and nothing else. A private subnet has no inbound internet route. Things that should never be directly exposed live here. Your application servers, your databases, your queues, your cache, everything sensitive lives in private subnet. Here's the rule. I will say it once and I want you to stick. If it doesn't need to be publicly accessible, it lives in a private subnet. No exceptions. Not even your dev environment, not even temporarily. The moment you put a database in a public subnet saying just for now, you have created a risk. Then we have the availability zones. Most cloud providers organize their infrastructure into availability zones, physically separated data centers within the same region, different buildings, different power, different network. In practice, you will create subnets across multiple availability zones. One public subnet in zone A, one in zone B. Same for private. This is how you get high availability. If one zone goes down, your app is still running in another. You'll often see this pattern: US East 1A, US East 1B, US East 1C on AWS. Three zones, your subnets spread across all three. Your VPN spans all of them. Oh, sorry, your VPC spans all of them. Route tables are the unsung hero that nobody reads until things break. Every subnet has a route table. A route table is just a list of rules that say if traffic is going to this destination, send it here. Example, your public subnet has a route that says traffic goes to 0.0.0.0/0, meaning anywhere on the internet, goes to the internet gateway. That's what makes it public. Your private subnets route table does not have that rule. That's what makes it private. Not a setting called private, just the absence of the route to the internet. Route tables are where a lot of misconfigurations hide. You set up a subnet, forget to update the route table, and your traffic goes nowhere. Or worse, it goes somewhere it shouldn't. You have a VPC, you have a public subnet and a private subnet. Now you need to actually let traffic in from the internet and let your private services call external APIs. This is where three pieces of infrastructure comes in. First one is internet gateway. The internet gateway is the front door of your VPC. It's attached to the VPC, not to any specific subnet, but only subnets with a route pointing to it. The public subnet can use it. It handles both inbound and outbound public traffic. Users hit your domain, DNS resolves to your load balancer's public IP. That traffic comes through the internet gateway, hits your load balancer in the public subnet. Then we have the NAT gateway. Your app lives in the private subnet. It has no route to the internet, but it needs to call an external API. Maybe it's calling Stripe. Maybe it's pulling a software package. You put a NAT gateway in the public subnet. Y- Your private subnet's route table says traffic for the internet go to the NAT gateway. The NAT gateway sends it out, but using its own public IP, not the private IP of your app. The response comes back to the NAT gateway, which forwards it to your app. The critical thing, the NAT gateway only allows outbound initiated traffic, one way exit. That's it. Users on the internet makes a request, it hits your domain, DNS points it to a public IP. That public IP is your load balancer in the public subnet. It receives the request through the internet gateway. The load balancer forwards the request to your application server in the private subnet. The app server processes it. They might need to call the databases also in the private subnet. Private to private traffic happens, no internet involved. If the app server needs to call an external service, that traffic goes out through the NAT gateway. Response comes back response comes back in, app processes it, returns the result, and that's the loop. This is the section your team actually needs. Everything up until now was infrastructure. This is the operational reality, the stuff that breaks in production and takes hours to debug because nobody knows where to look. First, we want to talk about security groups. Security groups are virtual firewalls that you attach to individual resources, not subnets resources. Your database has a security group. Your app server has a security group. Your load balancer has a security group. A security group is a list of rules. Inbound rules say what traffic is allowed in. Outbound rules says what traffic is allowed out. Here's the key behavior. Security groups are stateful. Stateful means if you allow inbound traffic on port 443, the response is automatically allowed back out. You don't have to write a separate outbound rule for the return traffic. The security group tracks the connection state and handles it. So this is a bit, or this is partially true. Like in AWS, you have both inbound and outbound rule. It depends on which system you are using it. Instead of whitelisting specific IPs, you reference another security group. You say allow port 5432 from app server security group. Now, any resource in that security group can connect. You add a new app server, it automatically gets access. This is how you keep rules maintainable at scale. Then we have the NACLs, Network Access Control List. NACLs are the subnet level versions of a firewall. They apply to all traffic entering or leaving a subnet. Key difference from security groups, NACLs are stateless. Stateless means both the request and the response need explicit rules. Allow inbound on on 443, great, but you also need an outbound rule for the ephemeral port range that the response travels back on, otherwise the network traffic gets dropped. This is why NACLs silently break things in ways that are incredibly hard to debug. Security group looks fine, route tables look fine, NACL is quietly dropping the return traffic. NACLs are your last line of defense at the network level. Know they exist, know they are stateless, keep them as a failsafe, not your primary control. Private endpoints. This one is huge in enterprise client environments. Your app in the private subnet needs to talk to your cloud provider's object storage. It can be S3, Azure Blob, GCS. By default, that traffic leaves your VPC, travels over the public internet, and comes back. That's a problem for clients with compliance requirements. So, healthcare, finance, government, banking, they cannot have sensitive data traveling over the public internet even for a millisecond. Private endpoints solve this. You create a private endpoint inside your VPC for the cloud service. Traffic from your app goes to the private IP, stays entirely inside the VPC, reaches the cloud service without ever touching the public internet. Now, DNS inside private networks. This one kills Team silently. I have seen it take days to debug. When you create a private endpoint, you want the host name to resolve to a private endpoint's private IP, not the public IP. This requires a private DNS zone that overrides the public DNS entry. If that private DNS zone is misconfigured or missing, your app resolves the host name to the public IP. Traffic goes out to the internet, and if your private subnet doesn't have a NAT gateway configured, connection fails. No error that says DNS configuration, just connection refused or connection timeout. And you sit there wondering why everything looks right. So far, everything we have covered is inside one VPC, one network, one team. Real enterprises clients don't have one VPC, they have many different VPCs for different teams, different VPCs for different environments, prod, staging, dev, and often they have on premise infrastructure that needs to connect to the cloud. Hence, VPC pairing comes into picture. VPC pairing connects two VPCs directly. They can talk to each other as if they are the same network using private IPs. It's simple to set up and works well for two or three VPCs. The limitations hit you fast though. VPC pairing is not transitive. That means if VPC A is paired with VPC B and VPC B is paired with VPC C, VPC A cannot reach VPC C through B. You have to create a direct pairing between A and C as well. At 3 VPCs, that's manageable. At 5 VPCs, you are writing 9 pairing connections. At 10 VPCs, you are managing 45. It becomes unmaintainable fast. Hence, we have a transit gateway, which has a hub and spoke type of architecture. This is what large clients actually run. A transit gateway is a central hub. Every VPC connects to the transit gateway, not to each other. The transit gateway handles all the routing between them. Want to add a new VPC? Connect it to the transit gateway, and that's done. Every other VPC can now reach it automatically through the hub. No new pairing connections. This is a standard pattern for organizations running 5 or more VPCs. If you walk into a client that has separate VPCs for dev, staging, prod, data, and security, they are almost certainly using a transit gateway or its equivalent. Then we have site to site VPN, very common in enterprise. Your client has an on premise data center, maybe a server room, maybe a legacy system that can't move to the cloud. They still need their cloud environment to talk to it securely. A site to site VPN creates an encrypted tunnel between the on premise network and the VPC. Traffic goes through the public internet, but it's encrypted end to end. Then we have the direct connect, express route, dedicated interconnect. This is the high end version. Instead of routing through the public internet, you get a dedicated physical fiber connection from your on premise facility to the cloud provider's network. No public internet involved at all. Maximum performance, maximum reliability, maximum compliance. You will see this at banks, large hospitals, government contracts. It's expensive, but for those clients, it's non negotiable. This is the quick reference. When you are on a client project and need to decide how to connect things, use this table. 2 to 3 VPCs, VPC pairing. 4 plus transit gateway. On-prem standard, site-to-site VPN. On-prem regulated, direct connect. Cloud service, no public internet, private endpoint. Private subnet needs external calls, NAT gateway. Everything we have covered up until now is mechanism. Subnets, route tables, security groups, these are tools. Now, this section is about why you use them the way you do, the principles behind the patterns. Defense in depth means don't rely on a single layer of security, stack multiple independent layers. An attacker has to break all of them to get to your data. In a well designed VPC, your database has at least three layers between it and the internet. Layer 1, it's a private subnet, no route to the internet. Layer 2, its security group only allows connections from the app server security group on port 5432. Layer 3, the subnet has a NACL with separate rules. Three independent layers requiring all three makes catastrophic failure orders of magnitude less likely, which basically means less risk. Principle of least privilege applied to networks. Only open what needs to be opened. Only between the resources that need to communicate. The common mistake is opening 0.0.0.0 slash 0. That's all traffic, any source. On outbound rules, to make it work, lock it down. Why a database must never be in public subnet? A database is public a database in a public subnet means it has a route to the internet. Even if your security group is restricting access, you now have a machine with sensitive data that is one misconfigured firewall rule away from being directly accessible from anywhere in the world. The architecture should make the catastrophic outcome impossible, not just unlikely. Zero trust. That's one sentence. Traditional security assumes if you are inside the network, you are trusted. Zero trust assumes the network is already compromised. Verify every request, regardless of where it came from. This is a section that will save you hours, maybe days. This is a checklist your team should have run on that client project. So, step one is, can the service resolve the host name? First thing before you touch any firewall or route tables, does it resolve? If not, the problem is DNS. Stop here, fix DNS. Everything downstream is pointless if the host name doesn't resolve. If it resolves, verify what IP is resolved to. Is it a private IP in your VPC range, or is it a public IP? Step 2 is, can it reach the IP on the right port? A raw connection test. If this succeeds, your network is fine and your problem is at the application layer. If this fails, continue the checklist. Step 3 is security group on the target. Look at the target's inbound security group rules. Is there a rule allowing traffic on the right port from the right source? Is the source correct? Is the port correct? Step 4 is security group on the source. Check the outbound rules. Hardened environments will have restrictive outbound rules too. Step 5 is route table. Is the traffic even trying to go to the right place? Most common problem. Developer moved a resource to a new subnet, forgot the route table update. Step 6 is NACLs. You have checked everything and it still doesn't work. Check the NACLs. Remember, stateless. The return traffic needs an explicit outbound rule covering ephemeral ports. Silently, no error, connection just hangs and times out. Step 7 still fails. Two possibilities. The problem is at the application layer, or you miss something. Start the checklist over slowly with fresh eyes. Network debugging is almost always one of these 7 things. The checklist is not optional, it's not for juniors. Run the list in order every time. You can refer to this screen, take a screenshot if you want, and I will move on to the next one. So I hope this video was informative for you. This was a very long video, and that was also my purpose, by the way. So from now on, I want you to look for other people who have shared much more detailed architectures on networking and be really informed about this stuff because this is very crucial. And one more thing is, when you start a project, sit with your client, uh, especially the client's networking team, and understand it properly so that your networking guys can configure things correctly and everything and all the traffic is flowing properly without any problem. So that's it. That's it. If this helped, share it with someone on your team or uh, or your managers for that matter. And I'll see you in the next one. Thank you.